Hello everyone, this is Logicless Coder, and today we'll start with the first problem of Project Euler. Project Euler has a series of mathematical problems which start are based on difficulty, and they add a new problem every few days. So we'll start with the first problem. It's marked as done here, but we'll take a look at this one. So it says, if you list all the natural numbers below 10 that are multiples of 3 or 5, we get 3, 5, 6, and 9. The sum of these multiples is 23. Find the sum of all the multiples of 3 or 5 below 1000. So multiples of 3 or 5, which is the number which is either multiple of 3 or multiple of 5 or both. The numbers, such numbers below 10 are 3, 5, 6, and 9. 3, 6, and 9 are multiples of 3, 5 is multiple of 5. And the sum of these four numbers, sum of the multiples of 3 or 5 below 10 is 23. We are to find the sum of such numbers below 1000. We can There are three ways I can think of to solve this problem. First one is the most naive way, which comes to my mind, is to iterate through all the numbers from 1 to 1000, go through all the numbers from 1 to 1000, and choose the ones which are either the multiple of 3 or 5 and add them to a number which keeps the sum of these numbers. This could be the easiest way to do this problem. It's like the naivest way, the first one which comes to your mind. So I'll just quickly take a look at code and how we can implement it in this way. So I'll take a number n as the limit, and I'll keep a sum at 0 for every number starting from, it can start from every number below 1000 if it's a multiple of 3 or if it's a multiple of 5. A number is a multiple of some number, it taken remain modulus with that number gives 0. Is the remainder of a number that is multiple of 3. The remainder of such a number with 3 will be 0. Same is the case of 5. So if it's multiple of 3 or it's multiple of 5, just add it to the sum, and then we print out the sum. We run this. We'll see the sum is 233,168. And if we time the execution, it says it was executed in 1.99 milliseconds, which is pretty fast because there are only 1000 numbers. And it is indeed the correct answer, 233,168. But if we take a closer look at the code of this problem, we'll see that we are going through all 1000 numbers, and we are checking if they are a multiple of 3 or a multiple of 5. We know for a fact that multiples of 3 occur at a distance of 3 and multiples of 5 occur at a distance of 5. So there is no point of traveling each number or visiting each number, because we not every number is gonna be a multiple of 3 or 5. So why even visit them? Why even iterate for those numbers? We can save some cycles by not iterating for those numbers. We can achieve that by, I'll make it as a function. I'll call it basic. Just takes in and I'll just write another function. Oh, what am I doing here? Right, so let's just write another function which saves some cycles or which doesn't iterate through all the numbers. So I'll call it like just so I guess which takes in another n and initializes the sum to be 0. And now we know all the multiples of 3 occur at a distance of 3, all the multiples of 5 occur at a distance of 5. So we can just count the ones which are start with 0, yeah, problem. And it should be n over here, should be n over here as well. Here, instead of incremented by 1, we'll increment it by 3. And then, since we are starting from 0 and incrementing by 3, this all these numbers are a multiple of 3, so you can just directly add them. Same thing we can do for 5. Since all these numbers, all the multiples of 5 occur at a distance of 5, we can just increment I by 5 and add that to the sum. We can return sum. Now we know for a fact that this function is correct, so we can just test the functionality or correctness of this function. So for that, we'll just assert if basic of n is same as master of n. It says assertion failed. We have made a very classic mistake in our implementation of the faster method. We are adding all the multiples of 3 here and are adding all the multiples of 5 here. So let's take a look at what numbers are being added over here. So currently we're adding here over here numbers like 3, 6, 9. We're starting from 0. We're adding 3 each time. So like 3, 6, 9, 12, 15, 18, 21, 24, 27, 30, like that. And over here we're adding starting from 0 and incrementing by 5. So we're adding 0, 5, 10, 15, 20, 25, 30, and so on. So the problem here is the numbers of multiples of 3 contain numbers like 15 and 30, and the multiples of 5 also contains the numbers like 13, 15 and 30. So if we, instead of checking for this assertion, just see out what we're getting, we'll see that we get a number 266333, which is higher than the number we got previously, 233168, which means we are adding something more that we should not be adding. And these repeating numbers like 15 and 30 are those numbers that we should not be adding, but we should not add because we are counting them twice. So there's one way to fix it. We can here like add a line here which says it's divisible by 3, then don't add those numbers because that have already been counted for. So I can just write if I modulo 3 is 0, if I modulo 3 is not equal to 0, which means if I modulo 3, then add those numbers. So now it will skip over these numbers and just keep on with the other multiples of 3. It will skip over 45 and go to 50. Skip over all the numbers of multiples of 3 which were already in this thing. We can take another approach by not doing this and instead finding all the multiples of 15, the LCM of 3 and 5. The numbers should be common in both the series will be the multiples of 15. So we can do it like this and subtract these numbers from this, and let's see if this works, gives us the answer we're looking for, and it does. So we have made a program, correct? We have made this function correct. But what makes this function faster? So this loop iterates for n number of times, 1,000 times. So it iterates for n times. This one iterates for n over 3 times for the first one, because we are adding 3 every time, n over 5 for the second one, and n over 15 for the last one. And if we were to take this part away and just use this method instead, we would say on these n by 15 iterations as well. Now it just iterates for n by 3 and plus n by 5 times. So it is iterating for far less times. So it should be visible in our time if we like if we time the execution of this one, we should see a decrease than 1.99 milliseconds. Let's take a look, and we do 1.83 milliseconds, and the difference is not that big. And for just 1,000 numbers, but if we're to say let's increase to 1,000,000 numbers, I think the sum would not be able to hold the sum in this case. But we don't care for the answer, we just want to see which one's faster. So in this case, if we compile it again and time both the approaches, you'll see the difference here. It says 2.99 milliseconds. And if we, instead of faster, use basic, time this, it says 5.5 milliseconds. So we are cutting down the time by, say, half almost, by saving upon those iterations while still giving the same answer. And we can do it even faster. We can do it, the fastest approach which we can go for comes from understanding the math behind these series and their sums. So this series is an arithmetic progression. An arithmetic progression is a series which has a form of something like this. It's the first number is a, the second number is a plus something, the third number is a plus second number plus something, which is same as writing a plus 2 times d. The fourth number is a plus 3d, and it keeps on going like that. It's an arithmetic progression. For a number like this, if there are like n terms, the sum of these n terms is equal to the sum of these n terms is equal to n over 2 times a plus n minus 1 times d. This formula is very well known in algebra, and it's extremely well commonly used because of how simple it makes things in dealing with arithmetic progressions. So in our case, we have 3 arithmetic progressions. One for the multiples of 3, one for the multiples of 5, and one for the multiples of 15, which we didn't use in this part to make it even faster. So if we were to use this formula to calculate the sums of multiples of 3 or 5, the answer that we require in this case, we would be calculating the sum of 3 for 1000 by 3 terms, like there are 1000 by 3 numbers, multiples of 3 till 1000, and then we're calculating the sum of 5 for 1000 by 5 numbers, because there are this many numbers, multiples of 5 till 1000, and then the sum of 15 for 1000 by 15 numbers. I can replace 1000 by n for generality, but yeah, we're adding the sums of 3, adding the sum of 5, and subtracting the sum of those 15 multiples. and that will give us the answer. Now this is a constant expression. Can be evaluated in constant amount of time. So this is O of 1, this is O of 1, and this is O of 1. So if we can calculate the answer without iterating over the number of n, so the time taken would not depend on n in those cases. So if I were to make a function which takes in, I'll call it s, and which takes in, I'll call it sum, which takes in a, d, and n, and spits out how many of those there are, sums there are. Our a is fixed, it's gonna be 0, so we can just skip that instead, and we can just write return n times n minus 1 times d over 2. This is what gives us in a small d. We asked to prevent from overflow in any case that may occur. And now we'll have the numbers, the sum of n numbers with the common difference of d starting from 0. So now we can just return sum of 3 for n over 3 terms, sum of 5 of n over 5 terms, and subtracted on sum of 15 with n over 15 numbers. So that's our sum. So we can just, here I'll just write it next to that, so that we can compare those two values and see if they're correct. Oops, okay, compiling it again. But as you can see, the values, they are not correct. There's a difference between these answers. It says 1014932684 9322675. Let's do it for 1000 and see what are we doing wrong. Where are we going wrong? So it seems like the second number of our, it's not adding a 9. It's not adding a 9, which means it's calculating something less than what it should have been. So the problem I think with that is coming from here. The number that we are passing in as the second argument. Passing in n by 3, n by 5, and n by 15 over here. This might cause a problem if the numbers aren't divisible by either of those. Say n is 1000. So we can calculate how many terms there are by taking a look at the generalized form of this one. So if we see an is equal to a plus n minus 1 times d. And now to find n, if we want to keep it less than, say, let's say a3, a of n, the a plus 0 plus minus 1 times, that is minus 1 times d should be less than 1000, which means d should be less than, n should be less than 1000 over d plus 1. This is what should be the lower limit of n. So in the case of 3, 1000 over 3 produces 333.33. So we'll round it down to 333 to account for that lesser than symbol. In case of 15 as well, because 1000 is not divisible by 15, we can do that. In case of n 5, since 1000 by 5 reduces 200, and then we add 1, it leads to n being equal to 201, which counts 1000 as well. So we can use this problem by doing this instead. So we can make sure that we never include and in our numbers. Oops, we're down even more. What is the problem here? I think there's something wrong inside here. A0. Oh, of course, forgot that one. Yep, we're good now. And if we time this for a million numbers, get 3.53 milliseconds, which is much faster than this. It's slower than this because it's not a big enough number. Let's say if we were to increase it even further more by going to 1000, a billion, 1000 million, sorry. And if we compile it again, and if we time it, you can see it executes in approximately the same amount of time, irrespective of what n is. It's because the complexity of this function, ignore the negative signs because you obviously overflowed. But the thing is, this one is O of n, big O of n, because it iterates, it scales with n linearly. This is big O of n because it scales with n linearly. This, on the other hand, is big O of 1 because it doesn't scale with n. It's constant expression, not a constant expression, but it's a just an expression, a formula which depends on n, which can be calculated in constant amount of time, irrespective of n. So this is the fastest approach. You cannot get any faster than O of 1. You can reduce the we can reduce the constants, but it won't make much of a difference. So yes, this is the fastest way to do this problem. The answer that leads to for 1000 numbers is 233168. So yeah, that was this problem. And I don't think like it was an overkill for such a simple problem. It was just 1000 numbers. We could have gone for even an n cube solution, which was of course not necessary. But yeah, that's the beauty of Project Euler. It's gonna get increasingly complex very soon. We need to be thinking as efficiently as we can from the beginning so that we are in the right mindset to tackle the next problems. So yeah, I'll see you in the next one.